All right, well, hello. We're going to go over homework 11.2, chords and arcs. And so we've got a couple definitions here and then two questions to illustrate two of the important theorems from this lesson. Again, hope you guys are doing well. We're almost there. A couple more of these and we will hit the summertime. Okay, so three definitions, minor arc, major arc, and semicircle. And so I think we can explain all of these simply just by drawing one big circle here. Okay, and so an angle, these all come from the center of a circle and then they extend outward like this. All right, and so this is what we call a central angle here, and then the area of the circle connected or included within that angle, that's known as the arc. So this is an arc created by this central angle. Central angles will always come from the middle of the circle. So once we look at that, we want to know the difference between minor, major, and semicircles. And that's fairly easy. That a minor arc, this right here, if I label this is point A and point B, this right here would be called arc AB. Okay, and so arc AB would be a minor arc. Why? Because a minor arc, I shouldn't actually put this here. A minor arc is a central angle that is less than 180 degrees. So in other words, this angle is less than 180 degrees, and so we call that a minor arc. So AB, for example, would be an example of a minor arc. To contrast that, let's say we do something like, we'll do this. I'll put a C here. Okay. Now again, so to continue to look at this one way, AC here, that would also be a minor arc because that's less than 180 degrees. However, if I were to say ABC, and so this arc all the way around this way, if I drew it kind of like that, that is over 180 degrees, and so that is a major arc. So that is a central angle greater than 180 degrees. And an example of that would be arc ABC. Notice if I say ABC to designate this angle, where if I could say ACB, that would be this arc here. If I said just with all these letters, if I were to just say AB now, it'd be a little unclear whether I mean this or this one here. Okay, so we could go ahead and put AC here. A to C is also a minor arc, but ABC is a major, or I could go ahead and add another ACB. The key thing is that they're over 180. Now, the easy rule of thumb is how do I know if something's over 180? Well, that gets us to a semicircle because 180 is half of a circle. Whole circle is 360, so 180 is the line that is a diameter that goes straight across. So this right here, let's go ahead and call this BD. Okay, BD, this is a semicircle. It's half of a circle. And so that's kind of in between. Just like when we did angles, an acute angle was less than 90, an obtuse angle was more than 90, and then you had right angle as the 90 degree. That's what this is. So a semicircle is an arc or a central angle equal to 180 degrees. And I won't make that any more complicated, but we'll say arc BD. Okay, so we have equal to 180, more than 180, less than 180. All right, now the two theorems, two questions. First question, within congruent circles, what is the relationship between their central angles, chords, and arcs? Okay, so let's differentiate those two things. So what I've done is I've drawn two angles, two central angles, angle AB and DC here. And it says, what's the relationship if they're congruent? Okay, so let's say this is congruent to this. Well, that means two other bits of congruency. One, Remember, a chord is a connection between two endpoints of a circle. And if the chord is formed by this angle, then that would be a straight line from point A to point B, or in this case, a straight line from D to C. And so all this theorem is saying is if I know these angles are congruent, I know that these chords are congruent, and then the arc formed by them is this out here. That's this distance between A and B, and that also is congruent. So I'll put two lines there. Sorry, it's a little sloppy. But the whole point is if, we'll just go ahead and let's see. Let's call this let's just say F. So the center point is F. So if angle AFB is congruent to angle CFD, which is what I gave you, that's the hypothesis. If these two angles are congruent, then AB, that's the chord AB must be congruent to chord CD, and arc AB, which is different. You have the straight line distance here, and then you have this curved distance here. So that's why these are not congruent. But arc AB is congruent to arc CD. Okay? And so that's all this question is getting at, is that these three things are connected to each other. That if you know the angles are congruent, then you've got the chords and the arcs, and vice versa. That if you have congruent arcs, then you also have congruent chords and congruent central angles. Okay? So the short answer to that, even though I think you should write this, is that they are all congruent. They are all congruent. By they, meaning central angle, chord, and arc. Those three things, if one of them is congruent, then the other two are as well. Okay, and again, that's just saying that if something's coming out at the same angle from the center, of course, that's a definition of a central angle, then it's going to, of course, create this opening as it opens up. These are going to all be the same. Okay, question number 2 asks, what is the relationship between a diameter and a perpendicular chord? Now I know you're just dying to know this. The relationship between a diameter. Okay, so let's draw a diameter straight across. That's a diameter. Cuts it into semicircles. And then a perpendicular chord. So if I want to draw a chord that is perpendicular to this line. So let's see, I got to make it at a T, so we'll do it like that. And so there we go, boom. That if you have a diameter, that means it goes through the center. Something going through the center, and then it's perpendicular to the chord. All you need to know then is that it bisects this chord. I know that this distance from here is the same as this distance to here. Or if I label these, let's call this A, B, and C. I know that. So if I need to, if the diameter is perpendicular to chord AC, then AB must be congruent. AB must be congruent to CB, here to here. Okay, so if you have a diameter that is perpendicular to this chord, then it's going to bisect these two things. Okay, so again, what's the relationship? Another way I would say it is the diameter bisects the chord. If it's a diameter and it's perpendicular. Okay, if I draw this chord at an angle and it's not perpendicular, well then obviously this rule doesn't hold out. And as for the converse of this is just reverse it. That again, if I have a bisecting and perpendicular line, then that line must be a diameter. So in other words, I could show you. I can illustrate the converse. this is actually kind of a cool way to, I think, to find the center of a circle, is that say I have a chord. I'll just draw it this way this time. Let's just do it this way. Right? If I have a chord and I find let's just say estimate, but I find the middle of that chord, because now I'm starting with it being bisected, and I go perpendicular, this line I've just drawn is a diameter. It goes right through the middle of the circle. So if you have a bisected perpendicular, the line that bisects and is perpendicular to a chord, then it is a diameter. So it just reverses this. Okay? But again, you'll see when you do the classwork, you'll use these two pieces of information, knowing that the angles, the chords, and the arcs are congruent, and knowing that diameters that are perpendicular to chords create two equal pieces. AB is congruent to BC. Okay, know that information until it's applied can be a little confusing, but jump into the classwork, and I think you'll see how it applies.